leave that up to you. We'll do a summary here of the entire chapter. Well, again, it's a summary, it's a recap, so we won't go over all the details. Again, I'll leave it up to you if you just want to watch and listen and think and nod along, like, yep, I remember that, I know that, and stop me if you've got questions. Or if you want to write it all down, because that helps you remember and learn what we're doing. I think like the title of the chapter is something like Applications of First and Second Derivative. So we didn't learn any new derivatives this unit at all. We only used derivatives. So in theory, we know how to take all the derivatives that we would use, and now we're going to use them in a couple of different ways. The first two things we talked about were Rolle's theorem and MVT. And each of those had an if and a then. So the conditions and the conclusion. The conditions for Rolle's were, continuous on the closed, differentiable on the open, and then what was the last one? Do you remember? This is the one that sets it apart from MVT. The y values at the endpoints are equal. F of A equals F of B. And while we're on the topic of conditions or if statements, the MVT was just continuous and differentiable. So that third part of the if for Rolle's is what made it Rolle's rather than MVT. What sets it apart. If we meet all those criteria, then the conclusion is somewhere the slope is 0. If the start and the end point have the same y value, then at least one place, in this case 2 places, have a slope of 0. And usually your job or the problem statement is to find C. Like find the place where the derivative is 0. You set the derivative equal to 0. So yes. And then be careful, you only pick the ones that are on your interval. The conclusion for MVT is a little bit different because you didn't have to have the same or equal starting and ending point. You could have different values for the ending point, the y values of the ending point. But the conclusion is calculus slope equals algebra slope. The instantaneous rate of change somewhere equals the average rate of change. And the average rate of change is just good old algebra 1 slope formula. So it's similar to Rolle's in that somewhere the derivative is equal to sort of the overall derivative. Right, there's the algebra rate of change, and somewhere right about there maybe the instantaneous rate of change equals the algebra rate of change. And again, your job is to figure out where that is. So you set the derivative equal to the overall derivative and figure out where C is on the interval. I guess we should, because if it's not on the interval, you can throw it out. All of that stuff was on the quiz that you now have back, so that's a good thing to review and look over. All right, then we did some first derivative things. And remember, f prime, y prime, dy dx, all of that's the same thing. That's all first derivative, different ways of writing it. And that equals the slope of f. I'm just throwing out some ideas here. That tells us if f is increasing or decreasing. Right? That's basically the same thing as slope. We can use it to find relative extrema. Right? If f prime changes one way or the other, we got a relative max or min. We can use it to find tangent lines. Use it to find critical points. We talk specifically about the first derivative test. That's where we set up a number line with critical points basically on the number line. And we look to see where f prime is changing from one sign to another. So what kind of relative extrema do I have at this spot?
You don't.
Good. Trick question. You don't. We go increasing, increasing. That's not a relative extrema. What kind of relative extrema do we have at this spot? A max, because f prime changes positive to negative. So when we want to justify a relative extrema, I would say f prime changes from, and then we have two options, right? If we go positive to negative, then that's a relative. Which one is that? If f prime changes from positive to negative? Max. Yeah, I mean, several of you drew the little thing with your hand. That's fine. Yeah, that's a max. And if it changes negative to positive, going down to going up, that would be a relative min. That's the first derivative test. You draw the number line, look for changes in the first derivative. And we had the second derivative, or f prime prime, as a few people called it, which is fine. That's accurate. You can call it f prime prime, f double prime, or y double prime. The notation's a little bit trickier, I guess, with the dy dx, because the 2 goes in a different spot, top and bottom. And what does if the first derivative, like looking for a parallel setup here, if the first derivative tells us the slope of f, what does the second derivative tell us about f? Concavity of f. So that's having to do with points of inflection. Concavity we already said. Remember, we can't say f prime is increasing or decreasing. That's the same thing as the second derivative, because increasing and decreasing is a derivative type word. So this is like a derivative of a derivative. We had a second derivative test for max and min. This is what people miss a lot, because what do you remember what you do first if you want to use the second derivative test? Right, take the first derivative and set it equal to 0. So it feels like misleading to call it the second derivative test, because your first job is to find where f prime equals 0. critical points. And then from there, if f double prime is positive versus f double prime is negative, that's our two different conclusions. So if f prime is 0 and we are concave up, but we're at a horizontal tangent line, what's the conclusion? What's the name of that point? A relative minimum. And if we're concave down, but also at a horizontal tangent line, that's a relative maximum. So it's called the second derivative test because we're using the second derivative to figure out if it's a min or a max. But we're not only using the second derivative, we also had to use the first derivative to come up with our candidates to figure out if they are maxes and mins. I'm going to draw this roadmap one more time. I feel like I've drawn it 100 times by now, but maybe that's because I have 3 calculus classes. Critical points lead to possible extrema. Critical points being where f prime is 0 or undefined. And then there's a 3-way fork in the road here. And they lead to different, or at least the top one leads to a different conclusion. Absolute extrema. So how do I test for absolute extrema? What do I do? Table of values. The critical points, but also with the endpoints. And I'm kind of running out of room here, but on that table, where do I put those different x values? Do I put them into f prime, or f double prime? F, because I just want to know who's the tallest and who's the shortest. So this is sort of the f path. The next two paths lead to relative extrema. First derivative test. That's the intervals on a number line. Looking for where we change from increasing to decreasing, that sort of stuff. So sort of the main one for that is f prime. And then our last path, the second derivative test. We evaluate the second derivative at the critical points and use the concavity to figure out, okay, are we at the top of a hill or are we at the bottom of a valley? And so you can use f prime, f double prime to find maxes and mins, depending on what kind of max and min you're looking for and what you do with f prime, f double prime. And then lastly, we spent a couple days on f prime, f double prime, on a graph or from a graph, depending on how you want to phrase that. I'll do one last table here, and then I'll answer questions. So I got a table with f prime being positive and negative, and f double prime being positive and negative. let's see, f prime. If f prime is positive, what does that mean about f? If f prime is positive, what can I conclude about f? It's increasing. So regardless of what f double prime is, if f prime is positive, f is increasing. If f prime is negative, then f is decreasing. F double prime, we already said, tells us concavity. So if the second derivative is positive, that means we're concave up. And if f double prime is negative, we're concave down. So if I want to sketch something that's increasing and concave up, can you draw that in the air? Increasing, but concave up. Yeah. Concave up. Yeah, there you go. Increasing, but concave up. Something like that. Next block over, well, no, let's stay with f prime positive. Let's stay with increasing. So f prime is positive, f double prime is negative. So I want increasing, but concave down. Increasing, but concave down. Draw it in the air. You see everybody draw increasing, concave down in the air. Concave down. There you go. Stay increasing though. Increasing, concave down. Next column, f prime is negative, so decreasing, but concave up. Decreasing, concave up. Good. Decreasing, concave up. And then lastly, decreasing, concave down. Decreasing, concave down. Yes, the people who are drawing it correct. People who aren't drawing it, I don't know. Decreasing, concave down. And so we can piece together things and sketch a graph based on that kind of information. All right, so that's a broad overview of what's on the test. But now let's turn our attention to the specifics of the worksheets I gave you yesterday.